before I start, let me introduce my fellow team members. On my right is Farhan, Xian, and Umarul. As a student, this object is the one thing that we are going to see in each and every day of our daily life. Classroom chairs and tables can be considered as an important element to improve and increase the comfort and focus of students while studying, in which comfort here does not only means by being ergonomic but also means strong and can stand high load that being applied, especially on the table part. This is because it is well known that usually the table part and sometimes the chair will be broken. Therefore, our group decided to make an analysis of finite element method on the table part of this chair. Our main concern is basically to study the behavior of the table when being subjected to impact loading. And the main objective of this project is to conduct a finite element method analysis by using FEMAP NASTRAN, where each one of us has already done our own analysis. And the second one is to formulate the finite element analysis for stress problem, and lastly to determine logical assumption on the value of deflection and also external loading and its point of application.
We analyze first. We mesh the chair with table, the overall part of chair with table. But actually, we encounter the problem while we trying to analyze the result from the overall analysis. Hence, we may analysis with only the table part. For our project, we investigate the table part because the table part of the chair with table is because it's always break and have the most critical part of the overall part. So the mesh start we analyze in tetrahedral form, and we have 4 different mesh analysis with 4 different elements and number of nodal analysis. Next, the boundary condition we use in this finite element project, we assume that the table is using the ASI 4310 because actually the table part is made of plastic, but in FEMAP NASTRAN we have limited in analyzing the mesh. We can only use steel instead of plastic. So the boundary condition for the table part, for the right side of the table, we assume that the part is fixed and attached to the frame of the table. So the Q is 0. Then we assume the load distributed among the top part of the table is 20 kg. I think that
Assalamualaikum. Good morning. My name is Umarul Aiman. So I will talk about the methodology about our project. So first process is we design the model using the SolidWorks. So before we put the model into the FEMAP NASTRAN, we need to design the model using the SolidWorks, which is we design overall part of the chair table, that is the chair and its table itself. And this is the view of the SolidWorks design. So okay, and then second one is after we finish design, we put it we will import it to the FEMAP NASTRAN. So the first process is we use to set up the geometry model, and just like what Farhan said, the part for the material part for the FEMAP NASTRAN is limited because it's only have steel but not plastic material. So we use for our scope. For our scope, we use AISI 4130 steel, and this is the details. So the young modulus is 2,900,000. The shear modulus is 0. Poisson ratio is 0.32. The expansion coefficient is 6.6 to the power of negative 6, and conductivity K is 5.55552 to the power of negative 4. Specific heat is 40.53, and heat generation vector 0. Mass density is 7.3314 to the power of negative 4, and reference temperature is 70. So for our project, maybe we just need to focus on the young modulus and mass density, I think. So and the type of material. So we move to the next slide. So for the modeling, we only choose the table part of the chair, that because for FEMAP NASTRAN we can't actually model the whole body of the chair, because to visualize the deflection, we can only see the specific part of the material. So we choose the critical part of the material, that is the table, because as already introduced in the introduction, because the critical part is when the table is when students put their head on the table. So the critical part may be at the center of the table. So we designed this table by using 3,962 elements in tetrahedral form. So the visualization is looks like this. Okay, so next. So after we visualize, we mesh the object, we put a specific load, and we determine the displacement of the material, of the object. So the distributed load we choose for this condition is 20 Newton, as told earlier. We choose this condition because it's almost the exact force as a human hand that puts on the table, and it's on the top of the surface of the table. So to make sure how to determine displacement, we also need to determine the boundary condition first after applying the load. So we fix at the bottom of the side plane here, and then the force will be around the square table here. So actually it's distributed around here, but mostly in the square part here. So as you guys can imagine, if we fix here and then force here, probably the most critical part will be here, and then the displacement here will. What I mean by applying the boundary condition is we will fix this position to be zero displacement, to be its fixed spot. So then, number 5, we will simulate the model and we will try to make the object move according to this displacement by the force it's already exerted on it. So after applying the load and the boundary condition, the result is kind of look like here. As you can see, there's quite big displacement here by the force that we have exerted. So actually, this one only just to show the movement of the plane by the force that have been exerted, but actually the displacement is quite small compared to this one, because as we told earlier, we are using a material that is steel, so it's impossible to have a displacement like this. So in reality, it will be only a little displacement if we use a steel, but if we use a plastic, like real life table chair, maybe it will be like this. So the stress value will be shown here, and this is in the unit of Pascal, and here is the number of displacement. So as you guys can see, maybe the slide that is showing the exact value, but the displacement here is around 0.0000583. So 0.000583 is quite a small number, which is what really, if we really use this, this will be the exact value of the deflection. But if we use plastic, maybe more value than this.
Go.
Thank you, Umarul, for giving us insight to how the simulation is made. As previously mentioned, there are conditions applied to our project. First of all, we only consider the table part of the chair as our analysis, because that is the most critical part of our project. We will first give you an insight on how our simulation is done, from the order of less element and finally the most element. First, we'll take a look at Farhan's simulation. He gave about 1,500 elements with a critical stress of 35 MPa and deflection of 5.57 micrometer. And here we can see that the overall picture is this part, right after the part where we fixed the table, is the place with the most critical stress. And then at the side of the table is where we get the most deflection out of the table. Next, this is Umarul's simulation. As you can see, he added another extra 2,000 elements. And what we can see here is we get a better picture of the stresses near the area where we are labeling it as the most critical stress. And here you can see that with the added elements, the deflection actually increased by a small margin. Next, this is more Aizat's element. As you can see, there's 30,000 elements with the most critical stress at 40.49 megapascal. So it's a very large increase from the less elements previously. Where you can see it's 4,351 elements. Now we could see it's 13,196 elements with the critical stress now becoming 40.49 megapascal. And finally, this is my simulation. where I put as much elements as possible, 78,173 elements. And here we could see, as proposed, here the table part next to the part where we fix is where we get the most critical stresses. And through my simulation with the most elements included, we can see the stress again increased from 41 to 45. And the displacement increased from 5 micron to about 9 micron at the edge of the table. After that, we will see a brief explanation or a brief representation of the number of elements versus the deflection at the edge of the table. As we can see, the higher number of elements, the higher the deflection it is. But this is due to the accuracy of the simulation with the increasing number of elements. Unfortunately, we didn't have the full version of FEMAP NASTRAN or a very high power computer. If not, we should be able to observe a flat line after a higher number of elements is implemented into the simulation. So now, all we can say is the higher the number of elements, the higher the deflection is. And the same story goes to stress. As you can see, the stress actually decreased from 1400 to 4,000. And then it kept on increasing until we reached a maximum level here. But as mentioned previously, the displacement haven't reached the maximum level yet, but the stress level has reached its maximum level. So from what we could see, overall we should have more elements in order to increase the accuracy of our simulation. Thank you.